Let's continue our discussion of the zero state response. This is from section 3.8 in your textbook, zero state response. A couple of additional topics that I want to cover out of this section. Of course, we calculate the zero state response by convolving the impulse response of our system with the input to get the output. So we looked at interconnected systems when we were discussing continuous time systems. So let's take a look at them. Their discrete counterparts. Actually, there's nothing surprising or new here. If we have two systems connected in cascade, one after the other, with input x of n, and then the output after passing through both systems we'll call y of n, and then letting h1 of n be the impulse response of the first system, and then h2 of n represent the impulse response of the second system. The overall impulse response is h1 of n convolved with h2 of n. So we can find y of n directly from x of n by convolving x of n with this h of n, which is obtained by convolving the individual impulse responses. The other case is the parallel system case. We have S1 and S2, and we sum their individual outputs to get the overall system output y of n with input x of n. It's easy to show in this case that the total impulse response is the sum of the individual impulse responses. Let's consider the step response of our system. So again, the impulse response is what we call h of n. H of n. And that's obtained when the input is delta of n. The unit step response is denoted by g of n. This is the output when the input is u of n. And then, of course, in the most general case, with an input x of n and output y of n. Of course, y of n is, of course, obtained by convolving x of n with h of n, the impulse response. So the impulse response allows us to find the output due to an arbitrary input. This is a special case where we've applied a unit step, and again we can find the output for any input by convolving that input, in this case the unit step, with the impulse response of the system. And this is why we place so much importance on the impulse response. We can use it to find the output due to any input. In this course, we won't put nearly as much emphasis on the step response. It is useful, but primarily in its relation to the impulse response. We can actually find h of n from g of n. Again, g of n is related to h of n in this manner, but we can also write that u of n, delta of n is u of n minus u of n minus 1. You should think about this. This is the unit step minus the unit step function shifted one sample to the right, so this difference just leaves a sample at n equals 0. Of course, that's our definition of the impulse response, but since delta n is related to the difference in the unit step by linearity, if we apply these individual inputs, we'll get out the response due to delta of n. So by definition, that's our impulse response. Of course, the response to u of n is what we're calling our unit step response. And by time invariance, the response to a shifted unit step is the shifted unit step response. So h of n, our impulse response, can be obtained from the step response by this equation. It's the step response minus the step response shifted one unit to the right. Another way to write this is we can write this expression as delta n minus delta n minus 1 convolved with g of n. Again, g of n convolved with delta n gives us g of n. G of n convolved with the shifted impulse just gives us the shifted function. So we can define then this as the impulse response of a new system. We'll call it, using standard terminology, a backward difference function or a backward difference system. So BDF here of n convolved with g of n, where h of BDF of n is defined as a system whose impulse response is actually delta n minus delta n minus 1. So this is the definition of a backward difference system or backward difference function. So we can then, in block diagram form, if we've got a system S and we apply a unit step to that system, we will get out g of n. If we then take the step response and feed it through a backward difference system, we'll get out the impulse response, h of n. Similarly, we can actually relate the step response to the impulse response. We can write u of n as this summation, the sum from k equal minus infinity to infinity of delta k. For all k negative, delta k is 0, so the sum is 0 from minus infinity up to k equal minus 1. Of course, at k equal to 0, delta is equal to 1, so for k summing from minus infinity up to 0, we get 1. And then similarly for all values of k greater than 0, delta k is equal to 0. So summing from minus infinity up to any positive value of k then would give us a sum of 1, and that by definition is the unit step. Again, we can invoke linearity here then to say that I can write u of n as a sum of another function, as a sum of other functions. So I can write the unit step response as the same sum of the response to those individual functions. Well, we know the response to delta k. That's our impulse response. Okay. So I can obtain the step response by doing this summation over h of k. And this is invoking linearity. And I can write this as actually sum from k equal minus infinity to infinity of delta k convolved with h of n. Okay. And so then I can define this term in parentheses as the impulse response of a new system that I'll call an accumulator. So I can obtain the step response by convolving the impulse response with this accumulator system. The impulse response of this accumulator system is, again, just this term in parentheses delta k. But we started this off by saying the summation is actually equal to u of n. So an accumulator system has an impulse response that is the unit step. Okay, and so if we run an impulse through this accumulator system, we'll get out u of n. If we run if we run an impulse through this system, we'll get u of n. If we run our impulse response through this system, we'll get out the step response of the system.